First up, we have David Holcomb from Oak Ridge National Laboratory. Many of you know David. He's been around salts for many years. He's got patents related to salt and instrument technology. So I enjoy working with him, and he is our chair for this conference, but he also has a presentation he would like to give. So go ahead, David.
All right, please bring up the first slide. Okay, I'm going to talk about fuel salt qualification methodology, and this is about realistically the fueled version of the fuel salt. I know we've also got unfueled salt as well. We're really trying to support, this is an effort that I, myself, George Flanagan, and Mike Poor have been working on for the last couple of years, and it's in support of the NRC where they are trying to look at a method or process for developing fuel salt qualification. However, this is my presentation, and so they don't necessarily endorse anything that's on here, that we are continuing this effort, and we hope to be supporting them in developing a new Reg CR under a new process, and from which hopefully they'll be able to develop some regulatory guidance. Next slide, please. So I'm going to try to explain why people are interested in fuel qualification, and it's largely because it's a very important part of providing reasonable assurance of adequate protection, developing the safety demonstration. Fuel qualification is a process which provides high confidence that with the physical and chemical behavior of the salt sufficiently understood, that it can be adequately modeled for both normal and accident conditions, reflecting the role of fuel design and the overall safety of the facility. Where uncertainties are defined, so the calculated fission product releases include the appropriate margins to ensure conservative calculations of radiological dose consequences. We've quoted that every time in all of the reports that we produce, because I think it's a really nice, succinct expression of what fuel qualification really is and why it's important. You can see that graphically here, where fuel qualification is an element of fuel performance. So you take an accident scenario, combine it with fuel qualification, fuel performance, along with the functional containments and the barriers to develop a source term, which then from the source term, you figure out how much of this is going to be released. And if you can reduce it enough, you get reasonable assurance of adequate protection. Next slide, please. No qualification method appropriate for liquid fuel salt currently exists. That's why we're working on this. There is a currently ongoing effort also to develop an advanced reactor fuel qualification methodology for solid fuels, and we are trying to structure this and don't do anything which is against that methodology, but the safety functions of liquid and solid fuels or it's not so much the safety functions, it's how they create the safety functions and how they realize them. Solid fuel does retain nearly all the radionuclides. They can't have leaks in there, but liquid fuel does sort of the same thing. It retains some of the radionuclides, but some of them inherently bubble out, particularly the gases and the solids. The solid fuel has to maintain a coolable geometry, while the liquid fuel is itself the coolant, and it has to transport the decay heat, as well as during normal operations transfer the primary heat. It needs to provide prompt net negative reactivity. That's provide the fundamental safety function of reactivity control. We need to provide net negative reactivity, but not so much prompt. And there, it needs to be before we actually have any damage out of things. So if you look at how you do existing fuel qualification, well, comes out of a number of different regulatory structures, whether it is New Reg 0800 and the descriptions of the core and the fuel, or Reg Guide 1.206. Well, they're all based upon the characteristics and the safety functions of solid fuels. The role of the liquid salt fuel plays in plant safety is significantly different. The physical and chemical behaviors are significantly different. Well, we started a few years ago and we talked at the RIC to some of the stakeholders, and they indicated, well, just trying to map the solid fuel requirements into liquid fuel would result in significant confusion and delay. So we're trying to, okay, let's see what we can do to apply the same safety philosophy, but to the actual physics and chemistry of liquid fuel. Next slide, please. Well, first thing to start out is, what is the fuel salt? When you look at a solid fuel, you sort of know what it is. It comes in discrete elements, rods and assemblies. And liquid fuel, it moves separately from its container or independently if it's contained during normal operation. Well, cladding and the fuel assembly structures are qualified as part of the solid fuel. Well, we again, in our opinion, and this is what we're moving forward with, is we're saying that because it moves independently of it as part of normal operation, the container and the material around it needs to be qualified separately. And that the fuel salt then therefore would include all the material containing fissionable elements or radionuclides that remain in hydraulic communication, but doesn't include the surrounding system structures and components. Things like salt vapors and aerosol would be considered part of the fuel salt until they become adequately trapped so that they're unlikely to return to the fuel salt. Container corrosion products become part of the fuel salt, while fresh and used fuels on site are required to be licensed, so they're part of the fuel salt as well. Next slide, please. Qualifications based upon, again, understanding the chemical and physical property of representative fuel salt samples. Aha, this is how it ties into that sampling project. We need to be able to look at particular samples. The liquid state significantly changes the physical behavior of the fuel. Liquids don't accumulate internal stresses, so you don't have sort of this mechanical lifetime limit because it was bent too far or it swelled too much. There just aren't any history-dependent properties. And then the flow homogenizes the fluid properties so that there's not a position-dependent properties or size-dependent properties. So chemical and physical properties are set by the elemental composition and temperature, not so much the isotopic content. Well, that tells us is small, minimally radioactive liquid fuel salt samples provide representative physical and chemical properties. And it's important to be able to sample the fuel salt to be able to determine what the elemental composition is, but hopefully we don't need to determine the other things from the highly radioactive fuel salt. Next slide, please. Next slide, please. Liquid fuel qualification establishes acceptable salt composition ranges that maintain the safety functions. I mean, basically, we know as things fission, the composition is going to change. And so there's going to be some envelope of properties which is acceptable. Well, sort of where are the bounds of the envelope? Well, that depends upon both the operational characteristics and the safety functions. Well, we start with some of the properties like liquid salts, a Newtonian fluid. Heat transfer and fluid flow behave in well-known manners in Newtonian fluids. There are continuous variants in the physical properties with composition. This is not a very exotic material. The reasonable assurance of adequate protection derives from a combination of the measured salt composition and knowledge of the resulting chemical and physical properties. So how are we going to go ahead and determine the resulting chemical and physical properties? Well, you heard one of the first talks was about that fuel salt property database. Well, and that's the function of that is the relationship between the fuel salt composition and its properties. Next slide, please. The liquid salt property database relates the composition to the physical and chemical properties. The database development is underway, and you've heard the current status earlier today. Salt property measurement programs are in progress at a number of places. We're trying to see if we can't integrate those things to make some more rapid progress so that we collaborate rather than compete. The only thing I'll note is that I don't think anybody is currently including the minor constituent transuranic elements just because they are small fractions of the salt. So americium, curium, and higher. We do require appropriate quality assurance for both new and existing data. And that's one of the things, I don't think we had a lot of discussions about how NQA1 is going to be applied to this or appropriate quality assurance. And that is actually a campaign activity in this current fiscal year, is to look at quality assurance requirements. Right now, to start with, the database is sparsely populated. As you saw in Jake's presentation, there's a number of areas that we simply don't know yet. I mean, one example of this is, what's the lifetime of the salt? we don't know when or if it's going to become waste, because we don't know all these complex multi-component solubilities. If it's, after decades and decades of use, what does it, when does things solidify out? When do they, that we could filter out, but when does it get to the point where the viscosity or the melting point becomes unacceptable? So the safety evaluations in the accident models are going to be performed with bounding values to establish an acceptable performance range. And that means things like, well, gee, the viscosity, if it's less than this, well, the natural convection decay heat removal system performs adequately. If it's more than this, it doesn't. So therefore, you have to know the viscosity, and that's an ensemble property rather than a particular one of a specific composition. So we're going to add additional data to the database over time, and the goals eventually to only require a composition measurement, and then at operating plants, and then just look up the properties in the database, much like you do that with a materials database. Next slide, please. Okay, so we're going ahead and looking at how do the salt properties relate to the fundamental safety functions, things like net negative reactivity feedback. Some of these things are Doppler broadening and delayed neutron precursor motion and such. Well, parts of these things are going to be in the salt property database. Parts of them are going to be periodically measured. And so this is mostly an eye chart to just show you that the salt properties provide all of, are sort of at the core of the fundamental safety functions. There's not much more to that other than just saying that, gee, how do we determine radionuclide retention? Well, you just go look at, well, tritium, how did that tritium get generated, and then where does it go? And that's the point of this plot. Next slide, please. The fuel salt properties support modeling the reactor performance under both normal and accident conditions, because again, fuel qualification is not just accidents, it's understanding the performance under both normal and accident conditions. So heat transfer in a Newtonian fluid is determined primarily by the density, viscosity, and the heat capacity. Some of the other things, such as thermal conductivity and radiative heat transfer parameters, can become important in specialized situations, such as small channels or startup of stagnant flows. And so those are also things, but for the general purposes, we really want to know the density, viscosity, and the heat capacity very well. So you start with the fuel salt database. Composition gives you properties. Well, that feeds into the fuel performance. Well, you look at your accident scenarios and you look at normal conditions, and then you see how did you achieve the fundamental safety functions. So fuel properties are at a core of, to their fuel qualifications, at our core of understanding the fundamental safety functions. Next slide, please. Periodic fuel salt property assessment will be an element of reactor operations. Essentially, it's analogous to material surveillance coupons. Even in, we know a great deal about how the reactor pressure vessel steels are going to perform and how other materials are going to perform, but we still go ahead and pull coupons periodically just to look at, make sure that things are going along the path that we thought they were going to. That's comparing the measurement to the prediction. As long as you're following the prediction, then you can operate for the next interval of time. If you're not, you have to go ahead and figure out why, or you're going to require some enhanced surveillance. The frequency of the property measurement depends upon the potential rate of change and how close you are to the allowable limits. If some of these things we looked at quite regularly at MSRE. For example, the chromium composition was an indication of ongoing corrosion. Corrosion can be very rapid. On the other hand, things like viscosity, density, and such, we just didn't accumulate after 4 years, with the low power density system, enough of these to really require you to relook at that. I mean, the uranium content even was inferred from the reactivity impact. Turns out it was 1,000 times more sensitive because it's a fission reactor, and how much uranium in is it really impacts the reactivity. So we didn't end up even measuring it chemically. So there's a lot of these things are about what do you actually need to have it do. Next slide, please. Fuel salt properties, significant part of a mechanistic source term. Mechanistic source term is your big element of how much, what's your dose consequence? How much dose might you release? Well, advanced reactors, the NRC has been looking at these for a long time. We are not the first people down the street, so we look at what have they gone ahead and established as what advanced reactors required in order to use a mechanistic source term. Well, there's a SECI, which is the Advisory Committee on Reactor Safeguards position, or it's a staff position, it's endorsement of that, on requirements for advanced reactors to use a mechanistic source term. Basically, the performance of the reactor and the fuel under normal and off-normal conditions is sufficiently well understood. So that's why we're doing all these modeling and to permit a mechanistic analysis, is develop sufficient understanding of the reactor and the fuel. And then the transport of fission products can be adequately modeled for all barriers and pathway to the environment, including specific consideration of containment design. So we're going to be very interested in how the fuel reacts with the barriers and how accidents stress the barriers and how they might bypass the barriers, because the pathways, a lot of this is, gee, you've got a small pinhole in this and it's a liquid system. Well, a liquid system with a small hole in it is like a bucket with a small hole in it, and you can leak 100% past a small hole. So you're going to be very interested in bypass mechanisms in addition to breaches. The events considered in the analyses to develop the set of source terms for each design are selected to bound severe accidents and design-dependent uncertainties. Essentially, we have to provide an adequately conservative set of consequences, and then from there back out what do we have as required properties to say that we're going to have consequences less severe than that. Next slide, please. Again, fuel qualification is just one element of MSR safety evaluation. So you end up with fuel qualification, which is a big part of how do you understand a source term, and the licensing basis events are all tied into that for establishing what do you have to actually evaluate. NRC has recently approved, the commission itself recently approved Reg Guide 1.233, but you can use that or maximum hypothetical accident approach to identify licensing basis events. You use accident progression modeling and tools, so we'll need full developed set of tools to go ahead and see, okay, given this accident, how much is being released, and then evaluation of the barrier performance, because that's a major part. If you've got an adequate set of multiple barriers, that's your defense in depth, that substantially influences what is your background, your net, say your mechanism, your source, which is your dose consequence, which is the negative thing you get from operating a reactor. Then advanced reactor siting criteria are based upon radiological consequences from design-specific characteristics. So that means that we need to have tools which are capable of being used for multiple different MSRs because we have multiple different designs. There are some possibilities of doing some bounding simplifications based on the class of reactors and the much simpler configuration of molten salts as compared to some of the existing large light water reactors, which have very complex interactions because of the amount of stored energy within containment. And that's all I've got. And so I think I have a little bit of time to answer questions.
Yeah, David. Thank you. We do have a question there. If you can see it, I will read it. It's from Brandon Chisholm at Southern Company. He's asking if there's been any analysis to understand the acceptable levels of measurement uncertainty.
Some of the modeling tools are being developed. Lou will have some discussion of that in the next presentation, but it's really just starting. I don't think we've got good answers to that yet on there. And uncertainty quantification and the impacts of uncertainties are part of this current year's MSR campaign activities. So this is an ongoing activity, and we don't have a really good set of answers to that. And that's going to be, you're going to run accident progression models with bounding things, which will determine what the uncertainties really are.
Okay. And one quick question, maybe is the Reg Guide 1233 publicly available?
do a quick Google, it'll show up on there. It's in NRC Atoms. It's a major, it was one of the major things that came out of the NRC this year.
Okay, yeah, I assume so as well. Okay, well, thank you, David.